All right, let's get right into it. Blue-green deployment, what senior engineers know that most developers don't. Welcome to this explainer. Today, we're totally tearing down those textbook deployment fantasies. We're going to look at the gritty, reality-based truth of what actually takes down your production environments. Because let's be honest, the theory rarely matches reality.
Picture this. It's Tuesday, 2 p.m. One of your devs merges a critical feature into the main branch. And the CI/CD pipeline, it runs flawlessly. I mean, 1,500 unit tests pass, the integration suite is 100% green, and the deployment to prod is a total success. Everything looks absolutely perfect. But exactly 5 minutes later, your checkout page starts throwing 500 internal server errors for 20% of your users. The pipeline literally just told you the code was safe. So what happened? Why is production crashing?
Well, this brings us to a quote and honestly a core philosophy we all really need to adopt. A senior engineer knows that a test suite is just a theory, only production is the truth. A junior engineer looks at passing mocks and just assumes, hey, it's safe. But a senior engineer, they know a test suite is really just a hypothesis. It's an educated guess running in this pristine, synthetic vacuum where users miraculously always click the exact right buttons. The second you release that code, your nice little theory collides with the messy, completely unpredictable reality of live user data, massive traffic spikes, and those lovely hidden race conditions. Bottom line, only production is the truth.
Take blue or green deployment as a prime example. The textbook definition sounds like an absolute dream, right? You spin up two separate but identical environments, you run your current app in the blue one and deploy the new stuff to the green one. Once green is healthy, you just flip the router switch, and if things go south, boom, you instantly flip back. It promises zero downtime and instant rollbacks. It sounds foolproof. But as we're about to see, in the real world, this theory can just completely fall apart.
You really have to notice the stark contrast in perspectives here. Junior reality says, mocks pass, code works safely. Senior reality says, real data fails due to environment mismatch and secret desynchronization. You see, the textbook completely assumes you have identical environments, but any senior engineer will tell you that environment parity is almost always a total myth. We call this the green pipeline false positive. Your code works flawlessly against the staging DB schema or the staging API mocks. But prod? Prod has slightly different configs, maybe secret desynchronizations, or totally different payload structures from third-party APIs. The code itself is actually fine. It's the environment context that triggers the failure. Let's watch how this snowballs into an actual catastrophe. This is a real-world ticking clock incident that we call the environment bleed. Check this out. 10 a.m. You trigger a routine Helm deployment strictly for staging. No big deal. But at 10 and 10 seconds, alarms start blaring. Your prod monitoring dashboard lights up red. The prod Redis cache hit rate just instantly drops to 0. By 10:01 a.m., the production database is absolutely suffocating under a thundering herd of requests, and CPU spikes to 100%. You deployed to staging, but you just somehow nuked production. How on earth does that happen?
The answer here is the isolation illusion. Look, in a lot of architectures, VPC peering exists between staging and production. Maybe it was originally set up just for database replication or something. But when an automation script in a staging CI/CD runner has a hard-coded default, or say it hits a logic leak in a Helm hook, it doesn't just fail gracefully, it fails open. It reaches right across that network connection and flushes the production cache. Relying on shared state or default configs instead of hard, physical network boundaries is a massive architectural flaw. So how does the senior engineer fix this? Simple. You build walls that absolutely no script can climb. Step 1, network segmentation. Just delete the cross-environment VPC peering. Get rid of it. Step 2, IAM scoping. You need to enforce IAM roles for service accounts, or IRSA, to guarantee your staging runner has zero network permission to even touch prod resources. And step 3, use tools like kubelinter to automatically scan your Helm charts and shell scripts for any hard-coded production strings. Seriously, if you take one single thing away from this section, let it be this. Never ever allow automation to have a default that points to production. All right, let's pivot to another absolute nightmare scenario. It's Friday at 4 p.m., because of course it is. You deploy version 2.0 of your service. Almost immediately, it fails due to a critical business logic bug. But hey, no problem, right? You just hit the rollback button in Argo CD to revert back to version 1.0, which was perfectly stable. But instead of fixing the issue, your error rate instantly shoots to 100%. Version 1.0, which was perfectly healthy an hour ago, is now permanently crashing on startup. Why did a safe rollback just completely destroy the system?
This right here perfectly illustrates a terrifying concept, the point of no return. You see, automated rollbacks only revert stateless code. They do absolutely nothing to automatically rewind stateful layers. Think about it. If your version 2.0 deployment included a database schema migration, maybe dropping a column or renaming a table, your database has permanently moved forward. When you roll the application code back to version 1.0, that older code wakes up, looks around for the old database schema, doesn't find it, and immediately crashes. To prevent this, we have to stop relying entirely on these autopilot rollouts. You need to put a migration sensitivity audit right into your deployment pipeline. If a release contains a database migration, a senior engineer needs to manually perform a destructive verification to check if that change is actually backwards compatible. And if a destructive change is absolutely unavoidable, the team has to formally acknowledge they are entering a no rollback zone. And frankly, nobody pushes that button without an airtight emergency recovery plan.
Okay, curveball time. Let's say instead of blue/green, you're using canary deployments because you want to be extra safe. Smart. You route a small chunk of traffic to the new code. The canary is totally healthy for 30 minutes. You're feeling confident, so you roll it out to 100%. But an hour later, the entire system crashes with an out-of-memory, an error. You tested it with real traffic, so what exactly went wrong here?
The answer comes down to understanding systemic behavior over time. Memory leaks are cumulative. A 30-minute canary window is just way too short to detect a leak that actually takes 2 hours to completely saturate the heap. The senior fix here? Your canary soak time has to be directly proportional to the application's expected memory growth rate. Plus, if you want to catch those silent bugs and nasty race conditions that local mocks completely miss, you have to bridge the gap between CI and prod. You do that by implementing shadow traffic replay using tools like Go Replay. You essentially capture messy, real production traffic and replay it against your new code in a perfectly safe staging environment.
Now this brings us to a really fascinating trade-off when we talk about achieving build perfection. Senior engineers love to strive for hermetic builds. These are builds that are totally insensitive to the host environment, basically guaranteeing 100% bit-for-bit reproducibility anywhere, anytime. It's awesome. But the trade-off is what we call the cold start tax. Pulling fresh runners and rebuilding from scratch every single time can easily bump your build time from, say, 5 minutes up to 25 minutes. To survive that, you have to aggressively mitigate the tax by setting up remote caching. Use GCS or S3 backends for Docker Build Kit or Bazel, and pull only the compiled blobs you actually need over the network.
All right, up to this point, we've talked a lot about adding things. Adding guardrails, adding tools, complex CI/CD machinery, the whole shebang. But let's shift our mindset entirely for a second. As the dev community profoundly pointed out, senior developers don't write better code, they delete more of it. I love this. Your real value as an engineer isn't in building increasingly bureaucratic delivery engines or showing off that you know the absolute latest framework. It's about systematically eliminating complexity and just drastically reducing cognitive load.
Think of it this way. Every single line of code and honestly every complex step in your pipeline is a massive liability. It's a potential bug, it's a maintenance cost, and it's a drain on your team's working memory. We need to start tracking the lines of code we remove, not just what we write. Keep the 10x rule in mind. Every single line you write is going to be read 10 times, modified 3 times, and debugged twice. So delete that unused endpoint, kill that outdated analytics dashboard, and absolutely eliminate those premature failover optimizations for scenarios that, let's be real, are never going to happen. So I want to leave you with this somewhat provocative challenge. The single most productive thing you can do to ensure reliable deployments isn't writing more code to monitor your code. It's writing less code that actually does more. The fastest way to ship features securely is to remove the barriers that are causing friction in the first place. Next time you sit down to architect a new deployment feature, or you're tempted to add a new gate to your pipeline, ask yourself, what can I delete instead? Rethink your architecture, drop the bureaucracy, and focus on owning a clean, highly reliable delivery engine. Go look at your pipeline today and find just one thing to delete. Thanks so much for watching this explainer, and I'll catch you in the next one.